Hey, what's up, guys? This is Dr. Vivek Palipuram, and I welcome you to ENGR 250 Probability and Statistics for Engineers and Computer Science. Well, my complete name actually is Dr. Venkataraman Vivek Palipuram Krishnamani, and whenever I introduce myself to students using this complete name, this is how they typically react. They're like, wait, what? What did he just say? So let me first give you a brief introduction about myself, and starting off with how my name actually evolved to being such a long name. So let's look into first evolution of Dr. Palipuram's name. So originally, my dad, Mr. PKV Raman, he named me as Vivek Raman. However, the school gave the government back in India my complete name as Vivek PKV Raman. So there's a practice in India wherein they usually attach the father's full name to the son's name or the daughter's name. So my name was augmented with my dad's name. So my complete name became Vivek PKV Raman, and that's what my government back in India they took my name as. Now it came the time for me to apply for passport so that I can travel abroad and pursue my higher studies. So in order to issue the passports, the governments usually do not take the initials. So they asked me to expand my initials. So I expanded my initials PKV, which happens to be Palipuram Krishnamani Venkataraman. But the government had their own plan to mess with my name, so they permuted my name and they took my name as Venkataraman Vivek Palipuram Krishnamani. Then back in 2008, I came to the United States to pursue my graduate studies in computer engineering. First, I joined Clemson University for my master's degree, and Clemson University couldn't fit my entire name, which is Venkataraman Vivek Palipuram Krishnamani. They did not have their systems capable enough to take my complete name, so they decided to abbreviate my name. So they also decided to mess with my name. So my name there was Vivek Chris Palipuram, and I happen to use this name for all of my publications ever since. The folks at the ECPE department there at Clemson University gave me several names. Some of them called me Vivek, some called me Chris, some called me Krishna, and so forth. As if it was not enough, I decided to pursue my doctorate in computer engineering, and my full name became Dr. Venkataraman Vivek Palipuram Krishnamani. And I can assure you that this is one of the most unique names you'll come across in reality, actually. So if you were to type Venkataraman Vivek Palipuram Krishnamani, it's going to point to just one single guy, and that's this guy sitting in Stockton, California. So that's how my name evolved to being such a long name, from a short, humble name, Vivek Raman, to Venkataraman Vivek Palipuram Krishnamani. So let me give you a brief introduction to what I have been doing so far in my career. So first, I started off as an instrumentation and control engineer. That's the degree that I obtained for my bachelor's, but I found my real interest in computing. So back then, when I was pursuing my degree in instrumentation and control, I was fascinated with microcontrollers and how they can control all these devices, and how microcontrollers and computing can actually be the brain behind the inanimate objects like robots or what have you. So I found my real interest in computing, so I decided to pursue my master's degree in computer engineering from Clemson University. But then I really got into computing, and back then high performance computing was at its peak. So I found my interest in high performance computing, and I decided to pursue my doctorate degree in computer engineering. I have extensive experience in coding scientific applications on supercomputers. As a high performance computing scientist, one of my roles is to port high performing applications to supercomputers, and these applications typically pertain to fields such as physics, chemistry, or even biology for that matter. I also have extensive experience in performing performance analysis, wherein I'm interested in predicting the runtime of these massive applications on supercomputing clusters. The applications that I work with would typically take several months, even up to years, to fully execute on normal desktop systems. My goal as HPC engineer or HPC scientist is to accelerate these applications and put them on supercomputing machines. But before doing that, one of the items that we typically perform is to predict how fast my application could possibly run on a supercomputing machine. Because when you consider supercomputing machines, they consume a lot of power, and poorly performing applications would actually mean more power consumed. So I use a lot of probability theory to predict the performance of these different applications that I'm about to port on supercomputing clusters. In fact, I'm also applying probability theory in my current research, which happens to be cloud computing. My research group is currently investigating how to recommend instances, cloud instances, or cloud computing machines to the end users for maximum application performance. Now, the problem is cloud computing has a lot of variance with respect to performance, because when cloud computing vendors, when they give out these devices, it's not only you that is active on that particular machine. In fact, there may be several other users that are actively using that virtual machine, and therefore your application performance is stochastic. It's not deterministic. It's variable. You may at times get really good performance. At times you may get really bad performance. Accounting this variance in consideration, my research group is devising machine learning techniques which are guided by probability theory to recommend the best possible instances for a given application so that the end user may reap the maximum benefits out of the given cloud instances. Essentially, they are able to get extremely high performance. So let's talk about the course goals and what you'll be doing in this course, ENGR 250, Probability and Statistics for Engineers and Computer Science. Just like how long my name is, even the course name is that long. So this course is actually divided into 3 phases. You have phase 1, phase 2, and phase 3. Phase 1 deals with hardcore probability theory, wherein you'll build a very solid probability foundation. And in this particular phase, I'm going to deal with a lot of mathematics, and I'm going to teach you different probability concepts, different techniques to solve probability problems. I'm going to introduce you to important concepts such as random variables, such as discrete random variables and continuous random variables, and distributions, probability distributions associated with them, which are typically used in engineering and sciences to model different stochastic or random events. Then from hardcore mathematics in phase 1, we are going to switch our gears a little to phase 2, wherein we'll be doing some mathematics as well as some amount of programming too. Now, if you are not familiar with programming, please do not despair. I'm here to teach you how to use these different tools to perform probability analysis. So I'm going to teach you essentially how to program specifically for probability theory. So in this way, you'll be able to exercise your programming skills and possibly also improve and pick up programming for your future courses. So let's talk about what you're going to see in phase 2. Phase 2 is going to be advanced statistics, where I'm going to discuss joint distributions, how two random variables together influence the outcomes of a particular event, and some distributions associated with them. We are going to see conditional distributions. These are some of the jargons that I would not discuss right now, but I'm going to discuss them in much more detail when we actually learn these concepts in phase 2. In phase 2, we are also going to pick up some programming to perform an important statistical machine learning algorithm called the principal component analysis. Specifically, I'm going to have you guys use principal component analysis to detect fruits in a given image. You're going to train your computer to automatically detect fruits such as tangerines or bananas or apples in a given image. Specifically, we are going to have our computer learn the statistical parameters of these different objects using principal component analysis, and we are going to detect some objects. So that's going to be really fun, you guys. Then we'll completely switch our gears to hardcore programming in phase number 3, where I'm going to teach you a new programming language called R, which is commonly used to perform statistics. I'm going to teach you R from bottom up, meaning that we are going to discuss the very basics of R all the way to some advanced concepts such as implementation of loops in R and how to use different functions to perform plotting and how to use R to perform some important statistical tests such as chi-square tests, performing some statistical inferences such as parameter estimation and hypothesis testing. These are again some of the jargons which will become much more clear when we actually look into phase 3. We are also going to use the R software to learn regression analysis. Regression analysis is a useful tool that is used to build predictive models so that you can predict the outcome given a set of independent variables. I have been using regression analysis quite a bit. In fact, my whole dissertation is based on developing performance prediction models for supercomputing clusters using the regression analysis. So I'm going to use some of that data for you guys to learn how to use regression analysis to create such predictive models. And if time permits, which I think it would, we are also going to see some advanced testing such as chi-square testing, which are quite useful for bioengineers. We are going to see random forest classifiers and naive-based classifiers as well, which are actively used by my research group to perform different kind of studies. So these are the course goals in detail. Phase 2 is going to take for us 2 weeks because to understand mathematics and to obtain that skill set of applying calculus to probability, it will take some time. Most of you may be computer scientists that may have not taken Calc 2 or Calc 3. Phase 1 does depend on Calc 2 and Calc 3, so we are going to take it easy. We are going to take up to 2 weeks to finish phase 1 so that you are up to speed with advanced calculus, specifically tailored for probability theory. So I'm not going to teach you the entire calculus concepts, but I'm going to teach you those specific calculus concepts that are particularly useful for the probability theory. Phase 2 is going to take us just 1 week because the concepts that you learn from phase 1 easily transitions into phase 2. And in phase 2, I'm also going to teach you how to use MATLAB to perform principal component analysis. And that can be a straightforward task because I'm going to have you guys communicate with each other and work on this assignment together. Then phase 3, I'm going to teach you R software. And since we are going to learn a quite substantial number of statistical concepts and statistical techniques, we will devote up to 2 weeks for phase 3. So phase 1 is for 2 weeks, phase 2 is for 1 week, and phase 3 is for 2 weeks. So I'm an engineer and we never joke about math. So our analysis will be highly mathematically intensive. So please make sure that you follow along, observe my lectures, how I work on different problems, and try to work on those mathematical problems just like how I have shown you in lecture so that you obtain solid mathematical rigor, which will transfer really well to your workplace as well. With respect to class policy, there's no textbook. I usually do not use textbook, but I give my students generous amounts of handouts and problems to solve. And we'll use office hours to discuss some of those problems that I give you for practice. So there's no textbook. I'll provide you plenty of handouts. For each week, I'll be posting an announcement, typically on a Sunday by 12 p.m., wherein I'll give you a set of lecture videos prepared by myself for you guys to review. And on Thursday by 10 a.m., you'll submit a problem that I will post on Canvas. Now, this problem will pertain to all of the lecture videos that I have given you for that given week. In addition to a mandatory problem that you'll have to solve and upload on Canvas, I'm also give you certain or several optional problems for practice as well. I'm not going to give you the solutions for those optional problems for practice, but I will have you guys visit me during my WebEx office hours and discuss those problems with me. So that's one of the incentives for you to attend my WebEx office hours so that you are able to discuss probability theory with me. Remember guys, this is an online version and I do not want a machine teaching you how to perform probability theory, but instead, I would like for you guys to solve certain problems and join me during my office hours as much as possible and solve some of those optional problems and discuss those problems. For each week, I'll have my office hours on Monday, Tuesday, Wednesday, and Friday from 11 a.m. to 3 p.m. This is going to be a recurring WebEx office hours. So all of you guys will get an invitation for this recurring office hours. You may either join these office hours if you want to discuss problems, if you want to discuss these problems, optional problems with me. Otherwise, you can just forego it. But my strong recommendation is for your in-class participation grades, please attend at least one office hour throughout the week just to have a discussion on probability theory and how is your understanding with respect to probability theory and statistics in this course. Every Thursday, we are going to have a WebEx class from 12 p.m. to 2 p.m. These WebEx classes will be recorded and I'll upload them on YouTube, or rather I will share a link with you for these recorded WebEx classes so that you can review. The reason why we are having these WebEx classes is to discuss challenging problems for that week. So whatever videos that you have viewed for a given week, that will all culminate to this particular class WebEx session, wherein we'll discuss much more challenging problems, which you may also expect in your exams. I strongly recommend that you attend the WebEx class. With respect to class policy, I highly encourage you guys to collaborate with each other for in-class participation problems that you will need to submit on Canvas, and for optional problems that you need to submit, that you actually do not need to submit. There will be just one in-class participation problem that you'll be submitting on Canvas, and there will be some optional problems for you just to practice. You can collaborate on these problems with your peers, but for your exams, you are going to typically be working alone, except for projects wherein I may have you guys pair up and work together. Engineering is a collaborative activity, so should learning be. So as engineers, we are going to collaborate and learn probability theory together. Let's talk about your grading. So there are going to be 3 exams because there are 3 phases. So exam 1 is going to be return only, and that's for 30%. The dates will be put on Canvas, and they are also on the syllabus when your exam is going to take place for exam 1. Exam 2 is going to be half written, half project, and exam 3 will be project only, where you'll be doing most of the programming. The weekly problems and office hours attendance will account for 5% of the entire grade. My grading scale is absolute, meaning that if you are between 93 to 100, then it's going to be an A grade. If you are between 90 to 92, then it's going to be A minus, and so forth. I usually do not curve the grades because I like for my students to strive for the maximum. Using this policy of mine, I have seen that a lot of students, it's not uncommon for a lot of students to just get A grades or A minus. So all of you try to do your best and shoot for the stars. So we are in this together, and we are going to have some fun with probability theory and statistics. So let's talk about what's all about this probability theory and really why it is important. Now, when I looked into the roster for ENGR 250, I found that there are a lot of students that are electrical engineers. There were several students that were computer engineers from computer science. Some of them were into bioengineering as well, and some of them were from engineering management. Probability theory is applicable for almost all the fields that you'll see in your day-to-day life. I can assure you that probability theory is prevalent in each and every field out there. For example, let's say that you're an electrical engineer, and let's say that you're designing a robot. So in order to design a robot and have it navigate through a path, people often use, or scientists or engineers often use, a technique called Kalman filtering, which actually relies on probability theory. Because using the probability theory, your robot is estimating where to go next, and it is going to go to a place where it is least likely to be slammed by some other objects. So there you go, guys. Probability theory is applicable in electrical engineering. For example, in Kalman filtering, there's an important assumption that errors with respect to estimation of the position of a robot is modeled using a Gaussian distribution. We are going to look into Gaussian distribution quite a bit of detail when we look, or when we study probability concepts in phase number 1. Let's say that you are computer engineers or computer scientists. You may be interested in stochastic behavior of computing. Sometimes your computers behave in an erratic fashion, and that's because there's a lot of things that are happening behind the scenes that are influencing the runtime or execution of programs on computers. Such phenomenon are stochastic or random in nature, and whenever there's randomness involved, you use probability theory to perform predictions. For example, I can use some probability theory concepts to predict what my application's runtime will be for a given application on a given computing system. Let's say that you're an engineering management graduate. You may be interested in using probability theory to study the amount of inventory that is coming into a warehouse, and you can use probability concepts to determine what should your next order volume should be, so that you are not wasting money on broken inventory or inventory that may potentially go bad. You may fine tune the amount of inventory you need using the probability theory. Probability theory, I think, is most applicable, or it has been never more applicable than right now. So we are amidst COVID-19 crisis. Epidemiologists and biostatistics use probability theory all the time to study how an epidemic is going to transform into pandemic. In fact, University of Texas at Austin has studied the probability of different United States counties to get high rates of COVID-19 cases. Probability theory is actively put into practice. In fact, in one of the phases, I'm going to give you a problem with respect to epidemiology so that you can really appreciate why probability theory is so much important, more so in today's time than ever. Okay, so that's the introduction to probability and statistics in engineering and computer science. I'm going to stop my lecture video right here. In this lecture, I introduced you to this course and we set our general expectations as to what we can expect from this course. In my next video lecturette, I'm going to discuss probability axioms and theorems, and we are going to discuss how set theory is used to find probabilities of different events. So now we are going to start our phase 1 probability theory. Thank you guys for listening.